I was hoping that the beers would be out by now, because this is going to be a gruesome talk. It has C++ in the title, but actually there's no C++ at all in this talk. The gruesome bits are the types. So yes, I work at Standard Chartered Bank, and just something about what we do. I work in the investment bank part, and we develop code for pricing and risk calculations. And lots of code is written in C++, and quite a lot of code. Our group has more code written in Haskell than in C++. We have about 2.5 million lines of Haskell code, and maybe 1.5 million lines of C++, something like that. We have, I think, about 20 people who program Haskell all day, and a number of other people who do it on and off. So we have quite a few people using Haskell. We do have our own Haskell compiler as well. So the Haskell code is sort of glue partly for all this C++ code that does the heavy lifting in computing prices and so on. And of course you want these calls into the C++ code to be as type checked as possible, so things don't go wrong at runtime. Well, by the way, if anyone has any questions, shout out and I will try and answer. Questions about anything. It doesn't mean I can answer them. So one very common library is one for relational algebra. So if you've done any SQL queries and things like that, you've seen sort of their perverted version of relational algebra. So I would say that ours is more true to the original relational algebra. So this is, the C++ code for this is dynamically type checked. So it means sort of you do runtime checks that you're using things the right way. And what I'm going to describe is how we put some static typing on top of that, so you can, when you use it from Haskell, actually get static checks, so you don't get these runtime type errors. And this static checked version is in daily use now. Yeah. So I'm going to talk a little bit about relations first, just so you have an idea. It really doesn't matter that this is a relational algebra package. It's just I have some functions, they do something, they are dynamically checked, and I'm going to, in words, describe sort of what the static things are that you would like to check. So I'm going to show you what the C++ API looks like without showing any C++. And then I'm going to talk a moment about some type system extensions that we're using to make this reasonably nice, the static version, and then show you just a few little fragments of what the statically typed interface looks like, because this library has a lot of functions, so I can only show you a few. And in there I will also mention something about type error messages. So if you can take away anything from this is the last talk of the day, so I don't really expect you to. But maybe a little relational algebra if you haven't seen any of that. Some magic Haskell type system extensions. And well, it's an example of using these fantastic extensions in some sort of real world example. So what is a relation? So a relation is a set of rows, and each row, you can think of it as a record. So it has sort of a bunch of named fields, and all the records have the same named field. So I mean, you can also think of it column-wise instead. So you have a number of columns, and they have names, and they also have types. So much better than describing this in words is to have a little picture of something here. A pointy thing. I used a hanger another. There are two relations, one called employee, and it has, so this is not part of the relation, not the name of it, but it has 3 columns, name, ID, and department. They have type, string, int, and string, and there are a bunch of rows. So Harry works in finance, I mean, if you want to have some interpretation of it. And there is another one containing departments. So these are the kind of things that we're going to operate on. But as I said, it doesn't really matter what these things are. It's just to give you some idea. There are a number of operations you can do. So union, for instance, you can have 2 relations, employee 1, employee 2. When you take the union of those 2, you get these. It's just what you think. You just put them both together. And if there are any duplicate rows in these, they disappear, because it's a set of rows, and the set only contains 1 of each thing. It's not multi-sets like many of these relational algebra query languages give you.
But only if the whole row is identical?
Row is identical.
Keys or anything like that?
There are keys. I'm going to leave out any talk about keys. But yes, the whole row should be identical. Intersection, similar to union, but you only get the ones that occur in both of them. Another common operation is projection. You pick out some of the columns. So for instance, if you say, I want to project only the department out of this, you'll get departments contains finance and sales, and here you can see you don't get finance twice and sales twice, you only get finance and sales. You can project out ID and department. You can rename columns. So this is really the operation that makes you want to use relations. If you're not going to use join at all in your code, you might as well use arrays. That's what I tell people who wonder why relations are good for anything. So join is a very powerful operation. So it will, in our version of join, it joins things by name. So these two, when you join these 2 relations, they have 1 common column, department, department. So you will get a new relation extended with sort of, well, it has the union of both these. And so you sort of look, okay, Harry and gets this ID, and he is in department finance. And then you find finance. If it's over here, you'll get George added to this, and so on. Sales get Harriet, finance gets George, sales get Harriet again. So if you sort of haven't worked with relations, relation join is really like function composition, even if you might not think of it like that. So what do I mean by that? Well, say that you pretend that these 2 are inputs, Harry and ID, well, name and ID are inputs, and this is an output. So I stick Harry and ID in there, the output is finance. So that was one function, and here's the other function. It takes finance as input and George as output. So you sort of do something with one relation, to put it together with another one, so it's really like function composition. But you keep the intermediate result here, which is department. You could also have an operation, or we have an operation called compose, where the department column disappears. So this is where the power of relation comes in, if you have an efficient way of doing this. Because the naive way would be sort of loop through all employees and all departments for every, and have some kind of n-squared behavior. But hopefully your implementation of relations are better than that. Yeah, this is just to illustrate that here finance has 2 managers, it seems, George and Eve. So that means that you get lots of duplication here, because Harry, who was in finance, finance is related to George here, and finance also related to Eve, which means you get both of those rows here. Again, what these things do doesn't really matter for what the main part of this talk. There are many other operations. I'm not going to talk about them. So the C++ API is strongly typed. So I mean, everything is type checked. It's just that it's type checked at runtime. There are only certain primitive types that we allow to be stored in these relations, because this is written in C++, so we are sort of restricted to what can be easily done in C++. Nicely, all the operations on these are pure, so if you take two relations and take the union, you'll get the new relation back. So there's no side effects, nothing sort of updates anything. So it was a very conscious decision in this library. They're all pure, so the Haskell types will look pretty nice for these. There's no I/O or anything like that. So I'm just going to show you first the untyped Haskell types for these, so to avoid showing you any C++. So here is a simple operation we can do that doesn't deal with the data in the relation at all. It's called header. So DREL is my type for dynamically typed relations, whatever they are. If you would think of how to implement this, it would sort of be all the function calls will be FFI calls into C++. So DREL will just be some kind of pointer into a C++, into C++ land where you have the actual data structure. You never marshal the relational data over to the Haskell side. It all lives in C++ all the time. So the header takes a relation and it gives you back the information about the names of the columns and their types. So string is the column name and type rep is this representation for types that lives in data.typable. How many people know about type rep? Fair number. Well, so it's just a representation of types that as a data type, so you can actually manipulate them. So if you ask for the header of this, you'll get, say, well, name is string. So this thing here, string, this is not a type, this is a type rep. I mean, it prints the same way as a type, and are named like the types are, of course. Nothing too strange about this. Well, most of these operations now in dynamically typed, they look like this. So union takes two dynamically typed relations and gives you another one back. But of course, things can go horribly wrong when we do this, because union only makes sense if they have the same header. They have to have the same column names and same column types. If they don't, there is no sensible way you can make a union out of them. So things can go wrong, and you get the runtime type error if you use union or intersection and so on with the wrong kind of relations, which is the thing we want to avoid in the end once we give better types to this. Well, I'll skip these, they're not that interesting. It's something you can think about. If you have no columns at all in your relation, so it's sort of empty, how many ways can you make a relation that has no columns? There are actually two. And well, join has the same type as union and intersection and so on if you do the dynamically typed version. But now the constraint here is a lot more complicated. So there can be overlapping columns now between the two relations. And if the columns that overlap, the sort of that have the same name, they also have the same type. You can't have a field called ID here that is an int and a field called ID here that is a string and try to join them. They must have the same type. And so you have two relations with two headers, and the resulting header is sort of, if you take the union of the headers, it has all the column names and column types that sort of are in both of them. No questions, I can just assume you're asleep. Here is the operation I showed you a little picture of, projection. So it picks out a number of columns from a relation, gives you back a new relation that only has those columns. So takes a bunch of strings, column names, dynamically typed relation, and another dynamically typed relation. And there are, of course, constraints. The projected labels, these labels that you mentioned here, they must be in the relation. If they're not there, there's something wrong. You shouldn't have duplicate names in here, and so on. So this function, as it stands here, there's no way to give this a Haskell type, the static type, I mean, because this relation, the output relation, it will have the columns that these strings say that it should have, which means that the type of this relation depends on the value of this. And types cannot depend on values in Haskell. You need a dependently typed language to do that. So if you had a dependently typed language like Idris, then you could make a sensible type here and have this be a list of strings and something complicated over here. So something we have to sort of, I want to have this operation, so we have to do something since Haskell can't have dependent types. And to give away already what we're going to do, this argument, which is a list of strings here, it's no longer going to be a list of strings. This is going to be some kind of type level representation of a list of strings, because types can depend on types, but not on values. So we have to encode these strings in some way so that they are actually types rather than values. Yeah, this, you saw this before. Rename, I'm going to skip rename. There are a bunch of functions that sort of operate on the values. I'm not going to show you the types of any of those in the strongly typed version, so I'm skipping this slide too. I only have so much time. So now you have sort of an idea of some of the operations in there. So now we have to figure out how to give better, stronger types to these. And before I do that, I'm going to describe the Haskell type system extensions that I'm going to use. And so I won't assume that you know about these, so I'm going to explain them. And well, we can start from the beginning. Kind declarations. So who knows about kind declarations? A couple of people at least. So you can have, in Haskell, you can have type signatures. You can say true has type bool. And in the same way as ordinary values, they have a type. Types also have a type, but they're called kinds. And so the type, also the kind that describes regular types is called star. So this is a kind signature. So here this is a value and this bool is a type and this bool is a type and this is a kind. And just as there are some kind of function arrows on the value level, so we can have a bool arrow bool value thing that takes a bool, gives you a bool. There are also star arrow star, for instance, which the maybe type has. So you give it a regular type, that star, and then you'll get the regular type back. But maybe itself has this more complicated kind, star arrow star. So standard Haskell only has two ways to build kinds. There is star, which is the type of regular types, and there is an arrow, so you can combine those in arbitrary ways. You might wonder, so if values have types, types have kinds, do kinds have something? Well, they're sometimes called sorts. I'm not going to talk about sorts, but and then it seems that people who do these things, they ran out of names, so I don't know if here's just some typical kind signatures. So yeah, I'm not going to. Okay, kind declarations. Who knows about kind declarations? Well, so you can't quite declare kinds in Haskell, but you can make new kinds. Who knows about making new kinds? Yeah, that's thinning out now in the crowd here. So let me give you the idealized version of this first. That's what's on this slide. This doesn't work in any Haskell compiler I'm aware of, but it gives you the idea, I hope. So if you want to make a new data type, you can say data bool, and it has two constructors, false and true. And if once you've said this, it gives you three things. It gives you a type called bool and two constants, false and true, that have type bool. So kinds were sort of the same thing, but one level up. So we could imagine that you could make a kind declaration, say, I'm going to define a kind called bool k, which has false t and true t in them. So this would give us a bool k, which is a new kind, and well, I do have a sort here. So this little square here, but can ignore that. And it gives you two new types. So false t and true t are types, but they're unlike regular types because they have this new kind bool k. So they're not types that have values in them. Only the star kind has types with values. These don't have values. So in some sense you can say this is just trickery to be able to compute things on the type level. And we need to compute on the type level because we don't have a dependently typed language. If we had a dependently typed language, we wouldn't have to use all this trickery. So this is the idealized way to write it. Kind, just like data, but it's instead of on defining a new type, it defines a new kind. So I'm going in a slide or so. I'm going to show you what it actually looks like in GHC, and you won't be happy. But Simon is back there. So there are also type level strings. How many here know about type level strings? Yeah. Oh, there's a few more. So a few versions ago in GHC, type level strings were introduced. So they're called symbols. So symbol is a new kind, and there is an infinite number of types that have this kind, and it's all the strings. So symbol is a new kind, empty string or empty symbol has kind symbol, and so on. So they look like strings, but they're actually some kind of types. But there are no values in these types. So they're just to be able to compute on the type level and have it look a little bit nicer. Also, they're quite convenient because all these infinite number of them, they all exist from the beginning. You don't have to declare them. They're just there. So we have an infinite supply of names here that we don't have to declare. These, yeah.
Sorry, why was quotes used?
Why was what used? Well, so they look more like strings. Unsurprisingly, I'm going to use these for my column names very soon. And so from my perspective, I think it's nice that they look like strings, but they could have, I mean, you could have picked anything. You could have, I don't know, do some lispy thing, have bars on each end, or start with a single quote, but that will soon be taken as well, as we'll see. I'm going to need the proxy type. How many here knows about the proxy type? This is more. So this is not an extension of any kind. It's just a module. It's called data.proxy. It has one data type in it, proxy A, and it has a constructor called proxy. This might look incredibly useless, but since we can't pass types to functions, well, not yet, as Simon mentioned this morning, there will be an extension to GHC soon, so you can pass types to functions. But since we currently can't do that, sometimes you really want to pass a type to a function. But we can't, but then we can use this proxy thing. So if I wanted to pass, say, an int to some function, you have to write this. It's a bit gruesome, but so proxy, that's the type, that's the value constructor, and it has type proxy int. So this type rep function, it's completely uninterested in the actual value of this. So I mean, it can only be proxy, so the value is boring. It's the type of it that is the interesting bit. So this is a little trick to be able to pass types when you really can't. And so if you just write this in ordinary Haskell, the kind of proxy would be star arrow star. But to make it even more useful, we want to be able to not only use regular types here, but maybe our symbols or something like that. So we really want proxy to be able to take any type, a type of any kind at all, not just star. So it's polykinded, which is like polymorphic, but one level up. So the kind of the proxy type is k, some arbitrary type, kind to star. It gives you a star back. That's the whole point, because things of stars you can actually pass around. Why did I mention this? Well, to be able to give you the type of this. So I showed you this, the symbols. So we have symbols. Sometimes you really would like to go from the type level. You have a type level string foo, but maybe you really want the value level string foo. And so this class ties them together. It says symbol val is an overloaded method, and it takes a proxy for the string, and it gives you a string back. Sorry, a proxy with the symbol, and it gives you a string back. And you can imagine there is an infinite number of instance declarations built into the compiler saying, well, for the type level string empty string, I will get the value level string empty string, and so on and so forth. So with this, you can connect the two levels. You can connect from having a type level string down to having a value level string, because sometimes you actually want to compute on the value level. Okay, so now we're back to the kind declarations that I had before. So here is one that I'm going to use. So you can make infix kind, well, ideally at least, you can make infix kind declarations. So I would like to make a new kind called field k that has two parts. So this is the new type constructor. And the first thing is a symbol and the second thing is a star. So this is going to be sort of the type of a column in a relation. I said a column has a name and a type. And we want the name and the type. So the type is already on the type level, but we want the name of the column to be on the type level too. So it takes a symbol, which is the name of the column, and the type of the column, and we get back some kind of new, something of a new kind. I could have used star for this too, but I like, just like you want to have as many different types for things as possible when you program in Haskell on the value level, so that the type checker can tell you when things go wrong. When I program at the type level in Haskell, I want things to have different kinds so that the kind checker will tell me when things go wrong. So how do you actually make kind declarations in GHC? Well, you can't. But you can have a data declaration, and you can, anything that is in a data declaration on the value level, you get some lifted versions of everything that goes one level up. So I'm not quite using the right notation. I'm using, I think some of these quotes are not necessary or are not even allowed, but I'll put them there to make things what I think is nicer presentation. So this is the ordinary data declaration in Haskell. And now from this, you also get a lifted version. So you get a new kind quote bool, and you get two new types, quote false and quote true, that have kind quote bool and quote bool. So everything is sort of one level up. So you can't directly make a kind declaration, but you can make a data declaration, and then you have the kind declaration automatically. I don't think this is a good idea, but who asked me? None. Because I don't want, for the things I'm going to do, I don't want the data type. I only want the kind, but I'm forced to make a data type. But I can't even make the data type that I want. I'll show you in a moment. This is just the same thing with a maybe type. Okay, so this is what I'd like to write. So I said, I can't write that in GHC. I might write the data declaration, and then I get something that's lifted. So I want symbol here, and I want star there. So what should I write here that lifts to symbol and something that lifts to star? Answer, you can't. There is nothing that lifts to symbol and star. So the people who designed this didn't really have sort of type level programming with new kinds in mind. It felt like they were just making something to sort of do some poor man's dependently typed programming. This is going to change in some newer version of GHC where types and kinds are merged. So then, but in the meantime, what do you do? Well, you can make a field thing that has two. This has two type variables. So I put the type variable here, and I put the type variable there. And now the lifted version, quote field X, I can pass in symbol, and I can pass in star here, and then I get the thing that I want. Oh, well, so that's not too bad. Let's just make a kind abbreviation, a kind alias for this, like so. No, that didn't work. GHC doesn't have these sort of kind synonyms, only type synonyms. Yet. But we have our old friend CPP. So I can define field K to be this application. CPP to the rescue again. Here is the most confusing one of them all. So this is what the data type of lists would look like if you actually were allowed to write this. So the type of lists has a nil constructor and a const constructor. And like all the other data types, this is lifted, so there is now a quote empty. That's the lift of the data type, so this is a new kind. And then we have two new types, quote nil, that's lifted of this, and quote cons. The thing that makes this confusing is that there are now 4 things called open bracket, close bracket. There is good old nil, there is the old type, the regular one, there is the one that is the lifted nil, which is not the same as the other one here, and there is the kind. So, I mean, at least there are 3 levels here. There are values, types, and kinds. So mostly there's not much of a confusion, except for the lifted nil and the regular old lists. So that's one of the reasons you might sometimes need one of these quotes to distinguish which one you mean. If it's the quote open close, then it means that it's the lifted one. And sometimes you're allowed to drop the quote, which makes things even more confusing. Okay, that was that extension. How many know about closed type families? Oh, that's impressive. So once you start this sort of programming on the type level, of course, you'll need functions on the type level. Well, there are already functions on the type level, but they're of this very peculiar kind that, like this. This is really a function on the type level. F, A, B, it does something. But the functions that already exist in Haskell on the type level, they all behave completely uniformly in A and B. You can't make a decision on what the right-hand side is supposed to be depending on the actual things passed in here. They're kind of like macros, they just expand it. So what we'd like to have is something like this. So saying, okay, f of int is Boolean, f of bool is string, and f of anything else is an int. This looks a bit like an ordinary function definition on the value level. So nowadays you can do that. It doesn't have that syntax, of course. Instead it looks like this. Type family f of a. This a here has no significance. Where, and then you give a bunch of equations saying, well, if I apply f to int, I'll get bool and so on. And doesn't have to be just kind star. Here is something that has some star arrow star kind of these and returns type level strings. So we're almost done here with extensions. Yeah, I'll skip this. Here's an extension that's not in GHC yet, so I don't expect you to know about it. Hopefully it will be in the next version, maybe. I promised to implement it, but I'm too lazy to do that, so someone else has picked it up, it seems. So in Haskell, you can write these operator sections, +1 times 2, which means this. So what might : int mean? I mean, it's not allowed currently, but if you just follow the same thing, it means this, of course, lambda x, arrow x, : int. So it's the identity function on int. So : t would be a short way of writing the identity function t arrow t. So, okay, I mean, it seems plausible extension, but is it useful? Yeah, I mean, not very, maybe at first glance. But you could imagine if I want to compose read and show, there's nothing that tells me what the type of the thing in the middle would be. Not that I compose read and show very often, but you could stick this thing in the middle because this is the identity function on int, so it's int arrow int, which forces the thing here to be an int. And I think this reads very nicely. Sort of, okay, you do a read, and then this forces it to be an int, and then I do show of that. Okay, so, but this is not the main use for this. I'm showing you the main use here in in the next slide. So type rep, this function that can give you a representation of a type back. It takes a proxy for a type and gives you a type rep back. Actually, the type for proxy is more, for type rep is more general than what I showed you here. It actually has a type variable here, so it's a proxy with small p, which means I don't necessarily have to pass something of type proxy with capital P here. I can pass any old type constructor. And so here is how you would pass an int in the way I described before. Take a proxy, and then you make a proxy, say it has type proxy int. But with the new signature sections, you can write this. Why? I mean, this looks very weird, because I said this has type int arrow int. That doesn't seem to be something that looks like proxy A. But it is, because, I mean, proxy A says it has to be something, and then it should be an A. So if we write out int arrow int, it's actually, without infix, it's something, an int, where this is arrow and int. So this unifies with proxy, and this unifies with the A.
That's toad.
Well, if there had been explicit type application, I would have used that. I think this is a beautiful hack. Okay, now, after having spent most of the time on not what the title of the talk was, I'm actually going to show you something about the strongly typed API. So we have to come up with some way to cleverly represent the types of these relations. Because you really want the people to, let me show you what some of them might look like. So here are some relation types. So these will be actual relation types. So these are now type level lists, and name is a type level string. Here's the triple colon we saw before. So name has type string, ID has type int, department has type string. And here's another one, which has them in some different order. And we would really like these two to be the same, because the order of fields don't matter. It's like records. Doesn't matter which order you put them. So we have to come up with some way to define this rel thing so that the order doesn't matter. And so we would really like to have a more advanced equality on types, where we can say, oh, the order in these things don't matter. But we don't have that. The only kind of equality we have available is structural equality. They have to look the same. So we have to do something different. We have to make sure that internally they are always sort of the same. So what I'm going to do is, there's going to be some kind of field sets. These are the ones that have a bunch of things in them. There will be a list of these field K things, but they will always be sorted in increasing label order. So internally, these will always be sorted in increasing label order. And then these will compare equal with ordinary Haskell type equality. Well, now we have to be careful, because if anyone can construct any of these field sets, we can't guarantee that they will keep them in order all the time. So this kind constructor, fs, will be hidden. It's the same way as you make abstract data types in Haskell. But now it's an abstract kind instead. So you can't construct fs yourself. All you have is this function that was provided to you that takes a list of these fields and returns a field set. And this function will order the labels and make sure there are no duplicates, because that's also not allowed. And then the actual type of relations, called relation, it's just a phantom type on top of the dynamic one. So it has a field set here. And to make things a little easier to write, there is a type abbreviation. Rel means okay. Oh, missing I here. Make field set. So I take these can be in any order now. This will sort them and then relation this. So which means these two will actually compare the same and this one's different. So this is really the trick. If not much of a trick, but yeah. Wait 1 or 2 slides. So let's program a couple of functions. So we want to be able to go between the dynamically typed word and the statically typed world. So it's easy to go from the static one to the dynamic one. We just strip off the new type constructor. But the other way, well, things can go wrong. So we can't have a total function here. So it takes a dynamically typed relation, and it returns a relation maybe if this fs thing really corresponds to what we have here. So if it's type correct, we'll get it back. Otherwise, we get nothing. So how do we implement type correct? Or what's the code for type correct? Yes. Well, I mean, if your use of this doesn't constrain fs in any way, then it's not going to work. But if your usage of this function forces fs to be something in particular, you could imagine some different version of this where fs is also sort of passed in as a proxy argument. Yeah. So this one works very well if you have a type signature right where you're using it, for instance. Okay, so we had the function header that I mentioned before. That was operated on the dynamically typed one. So the header gave you a list of string type rep pairs. So we have to check if the header that the relation actually has is the same header as fs describes. So we need some kind of function here, fields info, that takes an fs. Well, so it can't really take an fs because fs has type field set. We can't pass field sets around. It has to be type star. So it has to take a proxy fs and give you back one of these. And since we want this to behave differently for all the different fs, it has to be overloaded, so it has to be a class. So fields info will take a proxy fs, and it will give you one of these back. And, well, if it's the empty list, we get the empty list. If it has a type level cons, the thing here has a name and a type, and then we have the rest of the stuff. So we need to use symbol val. That was the thing that took a type level string thing down to the value. So we need a proxy for the name here. Type rep takes a type and gives you the value level representation of that. So that's the pair of the string and the type rep. And here's the recursive call that converts the rest of it. So here's the code that converts the dynamically typed relation to a statically typed one and gives you nothing if it didn't work.
So it was you added this as fields.
Yes, yeah. So yes, it was two polymorphic. Yeah, yes. Yeah, I left out a little bit. I seem to remember someone saying, these are all the constructors we have in this data. So here is a bunch of functions that are really easy. Union, intersection, difference, because they take two relations that have the same type and return something of the same type. So they just say something, relation R, relation R, relation R. So it's just a matter of stripping off the new type constructors and tagging it again and calling the dynamically typed version of these. So let's have a quick look at the make field set at least. So there are two things. They need to be sorted, and then there can be duplicates, and duplicates are wrong, so they should generate a type error. Okay. Sort by name. No, I don't have a type level quick sort. I have a type level insertion sort. Which I think for these this application is okay, because usually there are not too many of these, and if they're almost sorted, then insertion sort behaves quite nicely, and they're, yeah. This is, I mean, it looks a bit gruesome, but it's no more gruesome than writing the insertion sort as a value level thing. It's just that you have to do it on the type level, and there's a little more gunk around here to make it all work. Luckily, you can compare symbols to see if they're less than, greater than, or equal. The very last moment I made Javor Jaci add that to GHC just before the release of it, so I could actually do these. This was a few years ago, then I didn't actually use it for a while. Now, check for DUPs. Well, now they're sorted, so if there are duplicate names, they're going to be next to each other. So it just runs through them. It can be written nicely, more nicely with maybe with slightly different ways. So here, X and Y, we check if they're equal, if the names are equal. If the type, we don't care about the types, only the names. If the names are duplicated, it's wrong. And so if they're not, the names are not equal, then we just recurse. But if the names are equal, well, now we want to report an error on the type level. So something has gone wrong while type checking. So this is like the error. We want to use the error function on the value level, but we want it on the type level. And that wasn't there a few weeks ago, and I complained about it. And again, Javor to the rescue. He implemented this, and I think Simon is probably going to refine his implementation. But it looks something like this. Type error is the thing you can call on the type level when you want to report an error, and you can build them up by concatenation, and you can have bits of text. So this is a type level string, and you can take a type and you can turn it into something, whatever it is that you're concatenating here. So when something goes wrong, you will hopefully get an error message saying duplicated label, blah, and well, you'll get both of the duplicated ones. So it will say, if you duplicated A, it will say A and there, and it will say A there, at least with GHC. Yes, I think we do. But if for type level printf, we're also going, if we're going to have that to be reasonably smooth, we'll need some type level overloading, so we'll need classes on the type level. Is that coming, Simon, or is that? Yeah, so here is this new feature, which I think is absolutely necessary. Once you start doing advanced things on the type level, things are going to go wrong, and you need to be able to report errors. So as the final bit, I'm going to show you, I have 2 minutes, a type for project. I said we can't pass these strings here. That wouldn't work because it would be a dependent type. We can come up with a type that is cleverly different. So it takes a relation R into a relation S Which relation S? Well, the one we want. So what, with some restrictions. So the things that are in S, they have to be a subset of the things that are in R. And then I need this is fields thing because the actual implementation of it needs to get the names of the fields that we're going to keep. So this is a kind of an interesting way to write this because it no longer has that problematic argument. You can write one that has, you pass in a proxy for a type level list of strings there. But you can also do this. So this might force you to put a type signature on something here because, I mean, the compiler might be magic, but it's not magic enough to know what you're thinking all the time. You might have to put a type signature. Yeah, I'll skip this. And yeah, well, error message. Yeah, so here's just an example of what an error message can look like when once you've worked a little bit. I mean, you have to work a little bit in your type level programming too to be able to produce nice error messages. But for instance, if I'm trying to use a field that's not in some relation, so it could say something like field C type int is not in this relation. So the error messages look quite reasonable now. I spent a lot of time. So this is extremely tedious. I tried to make as many different errors as I possibly could and put them in a test suite and then run the compiler on all these different errors. And then I looked at all the error messages and I went in and tweaked the implementation of things until I got reasonable error messages for all of them. But of course, I'm not as ingenious as real users. They can make errors that I didn't think of. And there are still dark corners in the error messages now and then. Well, that was it.
Okay, we're running slightly late, but I think we have time for at least a few questions. Yes?
If you were to do it all over again, wouldn't you just have used a dependently typed language like Idris that you mentioned in the beginning?
We have 2.5 million lines of Haskell.
This is why you probably won't do it.
Yes. No, this would be much nicer in a dependently typed language. This is some gruesome workaround for not having dependent type. Partly, I mean. So, yeah, it would be nice to do this in a dependently typed language too. Yeah.
How do you write tests for your type level error messages?
I just have lots of modules.
But then you're expecting them to not compile, right?
Yes, so I have a little test script that compiles each of them, collects the error message, compares the error message to the ones that it generated last time to make sure there are no regressions in the error messages.
Right, so you can't express your unit tests in Haskell itself. It has to be...
No, there is a bash script.
You can using defer type errors.
We don't have that in our compiler because
Well, you should.
people
But
would
in-
misuse that.
But in GHC you actually can, and I mean I'm having libraries where I test for programs that shouldn't compile on the type level using defer type errors, and that works. It could be nicer, but it's a good solution.
Gershom.
So how are the compile times in your compiler for type level set? Is the performance okay when you're doing all this type level stuff?
I haven't compared. Our compiler is so slow anyway, so.
Okay, so it's a wash, I see.
Actually, the type checker is decent. It type checks like 10,000 lines a second, so.
Even with type level sets?
Yeah, I don't know. I'm the implementer. You have to ask a user. Ben.
Yeah, it's very
Well, I presume the programs you generate here take dynamic runtime input, right? Column names somehow. How does that work out?
Well, so mean, the code you've written, you probably have some static types in mind. So you get the dynamic relation from the outside world maybe. And then you use this, whatever I called it, from my relation, which was the one that converts the dynamically to the type to the statically typed. And if that fails, it means that the thing you got from the outside world didn't have the shape that you expected. And then, well, again, you have some kind of runtime error, or I mean, you can handle it in some way.
So the columns that you can work with are statically fixed.
They are, yeah.
So for a different different relational schema, you need to rebuild.
Yes, but you can write some overloaded functions that sort of are polymorphic in the names of the fields. So if say you want to take some column, multiply it by itself, and add it to the relation. So I mean, the actual names of the columns, they can be parameters to these functions. So you can write reusable code. You don't have to have fixed strings in there. They are you can have type variables that range over the strings after all. So, but yes, I mean, you can't really take anything super dynamic in and do sensible things with it.
One final question, perhaps. Thank Lennart again.